Welcome to Algebra 2. Today we're starting Chapter 11. Now, Chapter 11 is going to be kind of an interesting change for us. We're looking less at algebra than statistics. So some of you possibly looking at careers in business or nursing, things like that. A lot of statistics come into play in those professions, and to get there, you have to go through a lot of college courses based with statistics. So this is a very, very good chapter to introduce you into this other branch of mathematics, I guess you could call it. And really, it's very, very nice, kind of refreshing to get away from the algebra, all the rules that we've accumulated over the years, and kind of look at something new, a lot of vocabulary and a lot of analyzing. We hear statistics and data all the time in the news and online and things like that. And so it's nice to be able to have some understanding on how those numbers come about and then being able to analyze them. So to get this thing started, we are going to look at normal distributions. And I'm sure many of you have heard of the concept of a bell curve before, and that is a normal curve. So let's take a look. So what we're going to do is we're going to be looking at averages and probabilities. A normal curve is broken down, and I'm sorry if this isn't very clear on the video, but we have this center line where our bell curve is symmetrical on either side. And you can see it's labeled with this Greek letter mu, and that just stands for the mean average of our collection of data. Then what we do is we migrate out from that center symmetrical, most likely mean average that occurs most frequently. We migrate out in these divisions. So you can see that we are going from, oops, that's in the wrong spot. We are moving each time, in this case, 4 boxes on this little grid. But what they're doing is they're taking our mu and they're either adding or subtracting a lowercase sigma. Okay, and they're adding or subtracting that each time to come up with these divisions of our normal curve, our bell curve. And that sigma right here is referred to as the standard deviation. And it's just telling us if we have some value, how far is that away from our mean, our middle, our center of symmetry here. And in a normal curve, there are divisions that represent percentages, likelihoods, probabilities, depending on where our x value falls in terms of how many standard deviations away. So here's an explanation of what mu and standard deviation actually mean. The mean determines the peak of the normal curve, and we find that just how we were first taught to calculate averages. You add up all of our possibilities and divide it by how many there are. Not possibilities, how many, add up all of our data and divide by how many entries we have. Then the standard deviation, that lowercase sigma, that determines the placement of those increments along the x-axis. And it has a pretty complicated formula here, but it's kind of interesting. This square root of things squared, it's really kind of calculating a distance formula for us. And that's exactly what the standard deviation is doing, is it's moving these little distances away from our mean. So that's how we find the standard deviation. Do not worry, we are not going to have to calculate that. I'm just showing you where it comes from and kind of how it ties in. Now, not all data collected will represent a normal curve, right? You saw that perfect bell curve at the start of the lesson. It was perfectly symmetrical. So if we look at a histogram of data and see the frequencies of each of our outcomes, if that data represents a relatively symmetric, you know, the highest, the most frequency happens in the middle, then that means our mean, what's in the middle of our, you know, the average of our data, is equal to the median. It's equal to what occurs most frequently. So that is something that represents a normal distribution when we're looking at data. But it is possible that, you know, maybe our data is really heavy on the top end. That we say that that is skewed to the left because it tapers off to the left. It means that our mean is less than the median. So what we have as occurring or what we calculate as our average, is actually less than what's in the middle of all of our data set if we list it all out. And we could also have a skewed right. This means that a normal curve will not represent the data if we have a graph that is skewed to the left or to the right. All right, so why bother with the normal curve? Well, it makes calculating probabilities incredibly fast. So we invest a little bit of time to arrange our data in such a way to use a normal curve to represent it, to find that standard deviation, find that mean. And once we have that, we can use the symmetry of the graph of the normal curve to help us out. Right? So first of all, the total area under that normal curve is 1. Okay, so that represents 100% likelihood going all the way from covering all of our outcomes, the area underneath 1, representing the 100%. And then in a normal curve, about 68% of the area lies within 1 standard deviation. So that means if we have our mean going down the center, here we are, 1 standard deviation in each direction. That makes up 68% of all of our outcomes. Okay, 68% of that area. Okay, then if we go 2 standard deviations, 1, 2, 1, 2 from our mean, that contains 95%. And if we go 3 standard deviations away from our mean, that contains 99.7%. So having these possibilities makes it very helpful for us to answer what is the probability of choosing this object that's between this and this. Because now we have these increments that we can answer that between question very easily by doing just our simple and or calculations. Well, it could be this or this. So we add up those percentages. It's already probabilities for us. This is really, really nice in terms of making short work out of it. I would make special note of these percentages right here. So the picture off to the right, it basically breaks this normal curve down into little wedges, little slices of that normal curve, and it shows you the percentages for each of those wedges. So knowing these numbers is very, very helpful because those are the numbers we're going to be adding up quite a bit this lesson. All right. So our first example, here we have a normal curve and we have all the standard deviations drawn in. We need to give the percent of the area under the normal curve that's represented by the shaded regions, or as you can see in 10 and 12, maybe they're just describing the probability of a certain event, a certain range of events occurring. So for number 4, we take a look. I've got this little wedge and this little wedge. So I'm going to relate that to the diagram that we had just on the previous slide that says that this wedge over here that is 2 standard deviations away is 13.5% of the area. And then this one that is 3 standard deviations away is 2.35%. Okay, so the percent of the area is when I combine those two together, 2.35 plus 13.5, giving me 15.85%. You just add them up. For number 6, here I've got 2 wedges, and you can see why knowing each individual wedge's percentage of area is very, very helpful. Otherwise, we could always add and subtract away, the other pieces. But here we've got these 2 wedges, each of which contribute 13.5% of the area. So we know that the total area, total percentage of area is 27% when we add those up. And you can kind of just imagine that these normal curves have like a distribution underneath, like dice rolls or anything like that. So having our x-axis labeled with frequencies and stuff, we could say 27% of the time this or this will happen, which is really, really cool. It makes the math very, very short. Okay, number 10. Notice now here it's not the percent, it's the probability. So we're going to answer in both ways, but remember probability is a number between 0 and 1. We're going to probably leave our answers as decimals instead. So for number 10, let's read the event. The probability that our x value, we're still dealing with a graph, this is still an x-axis here, our x is less than or equal to the mean plus a standard deviation. Okay, so I'm just going to make a quick sketch here. Here's the mean, here's one standard deviation. We want our x value to be less than that, so we want all of that. And we're just kind of visualizing that in our heads. Okay, so what does that mean? It means I've got, probably switch colors here. It means I've got one of this wedge, one of this wedge, 2, 3, and then that little tail off to the end. Wow. Okay, so I would take 34% plus 34%, plus this one would be 13.5, plus this one would be 2.35, and this one would be 0.15. And if we total all that up, we get 84%. But since they wanted a probability based on how they've kind of expressed their region here under our normal curve, we would call that 0.84. But again, we just add up those probabilities using that chart that was on the last slide. All right, number 12, here let's make one more little sketch just to kind of show what we should be visualizing. So we want 3 standard deviations less than our mean. So there's 1, 2, 3, up till the mean. So now we want this wedge and that wedge. Well, that's a 34% and a 13.5% and a 2.35%. If we total all those up, we get 49.85%. 85%, or as a decimal, 0.4985. Okay, now this is all pretty abstract right now. We haven't attached it to any like concrete data or statistics from the real world, but being able to navigate these just using the language of a standard deviation and using the percentages of area offered by each wedge in a normal curve, that really helps us navigate. Then we can apply it to some situations. All right, so here we move another stepping stone forward. We have a normal distribution. They tell us the mean is 33 and a standard deviation is 4. Find the probability that a randomly selected x value from the distribution is in these given intervals. Well, I'm going to make one nice sketch. Again, the more we can visualize those wedges on our normal curve, the better off we're going to be. Okay, so there's that, just a rough sketch. And then if this right here is 33 and that is our mean, our standard deviation is 4, so let's construct our wedges here. I could be, one step above, so that would be 37, moving up one standard deviation, then move up again, that would be 41, move up again, that would be 45. Let's go down the other way and construct the wedges to the left. Be a 29, 25, and a 21. And you'll notice that I just moved 1, 2, and 3 standard deviations away, in this case 4 units away, in each direction from our mean. Okay, the same percentages still apply. It is a normal distribution, so we still have those same percentages that we get to fall back on. Now it's just kind of making the prompts in the problems match up with our little diagram here. So number 14, between 33 and 45. So that means, I'm going to try and do this in a way that I can reuse this diagram from here to here. So I've got 3 wedges to add up. I've got a 34, I've got a 13.5, and I've got a 2.35. Those are the percentages respectively, those 3 wedges I need to add up. That totals up to, okay, we're finding the probability, so we'll want it as a decimal, but we get another 49.85%, so 0.4985 is our answer as a probability, as a decimal. Okay, number 16, at least 29. Well, we got a couple different ways to look at this one, because here we want 29 and onward. So what do I have for wedges? Well, I've got the 2 big guys in the middle, and then 1, 2, and the little tail off to the end. So I'm adding up 5 numbers there. I've got a 34 and another 34. I'm just reading them left to right, and a 13.5 and a 2.35, and then that tiny little tail at the end, which is 0.15%. And if we total all that up, we get 84%, or as a decimal, 0.84. Now, some of these numbers are looking pretty familiar, but that's not surprising. We're using the same percentages each time when we're summing up these wedges, so it's not unlikely that we'll see the same answers resurface again. And lastly, number 18, at most 21. So at most 21, well, here's 21. That's the most that my x value could be. I want anything less than that. It's just the tiny little tail off to the left. That is a 0.15%. Nothing to add on to it, but as a decimal, for our probability, that would be 0.0015. Not very likely that our random x value is going to fall over there. Now, as you look at this, you can see the math is not very difficult when you step back and take a look at it. It's understanding how to navigate this normal curve. The math itself is really easy. It's the vocabulary, the language that's going to, maybe trip us up a little bit. We just want to be sure that we're reading the graph correctly. Okay, so we read the graphs, we understand the percentages and how to add them up. We looked at a situation that just dealt with numbers. Now let's apply it to a real-world situation. The times a fire department takes to arrive at the scene of an emergency are normally distributed with a mean of 6 minutes and a standard deviation of 1 minute. Okay? Before I start calculating anything like that, I want a visual. Let's make a little normal curve here and show our mean and our standard deviations moving away from that. We'll use red because it's a fire department, fire truck, fire engine red. So right here is our mean of 6 minutes. And then the standard deviation, the increments that we're going to use, we're going to go 3 standard deviations to the right. That's adding 1 each time, our standard deviation, and 3 units to the left, subtracting 1 each time. But that gives us the increments, right? That's kind of what we're describing standard deviation as, an increment for our normal curve to be measured in. It creates the wedges. Letter A says, for about what % of emergencies does the fire department arrive at the scene in 8 minutes or less? Okay, so here's 8 minutes or less. Let's take a look at all of our wedges that we've got to add up. We've got 2 of the 13.5s, 2 of the 34s, a 2.35, and one of those little tails, the 0.15. Just reading it from left to right, 0.15, 2.35, 13.5, 34, 34, and we had another 13.5. When we total all that up, we get 97.5%. So again, now if our if our graph represents all the different times the fire department was called out and the x-axis is the time it took to get to the scene, we randomly choose one of those calls. 97.5% of the time, they made it to the scene in less than 8 minutes. Very cool. Very cool. Very short work of a seemingly complicated problem. Letter B says the goal of the fire department is to reach the scene of an emergency in 5 minutes or less. About what percent of the time does the fire department achieve their goal? Okay, so now we're looking for 5 minutes or less. That's their goal. They're not quite, their average is 6 minutes, but their goal is 5 minutes or less. So their average is a little bit worse than their goal. We're not expecting a very high probability here. And we can tell that by looking at how much area the wedges we're going to be adding up actually take up in that normal curve. They don't take up very much of it. Okay, we've got our 0.15 tail, we've got a 2.35, and we've got a 13.5. That totals up to 16% of the time that fire department actually arrives to the scene in their goal time or less. Now you might look at that and think, oh, that's not very good. Well, think of everything that's involved. They got a lot, maybe they have to travel for more fires than they do for other ones. This is a nice way to represent their data and maybe have some good discussions. What's causing all of these 7 and 8 minute trips out to get to the scenes of the fire? So really good data to analyze, and you're able to analyze it very quickly. Now, what made that last problem very easy to navigate is that the value we were looking at, 5 minutes or less, 8 minutes, those fell on perfect standard deviations. That doesn't always happen. What if they said the goal of the fire department is to reach the scene of an emergency in 5.5 minutes or less? Or how often is that, what percentage of the time is the fire department there in under 3.5 minutes? Something like that. It's not as easy to do when we don't have those nice clean wedges to use. Well, in order to adjust our normal curve to work with any x value, we find out what's called a z-score for that x value. And that basically what that does is it takes a situation and it adjusts our normal curve. It standardizes it to work for us. Okay, so here, it's a very simple formula. I would definitely box this up. If we don't fall on an exact standard deviation when we're trying to calculate it, we need to run through a z-score for it. And all that does is that will adjust our normal curve to work with the numbers that our z-scores represent. All right. Once we have our z-score, it tells us how far above or below the mean we are. And then we'll fall back on a table. In this case, the textbook has us use a table to find the probability. And this is that z is less than or equal to blah, blah, blah. So based off of our standard curve, our standard wedges, we have these probabilities to work from. So let's say we're looking at an x value, and we find the z-score for that x value using that formula on the last slide. Say that equaled a negative 1.22. Okay, that's telling me that I'm negative 1.22, for my z-score. I'm less than my mean. So using the table, I would go to negative 1 and 0.2 to find out the probability. So the probability, or how much area that curve is taking up, that normal curve is taking up for that particular z-score or less, is 0.1151. So it makes it pretty easy when you think about it. There's a lot of math happening behind this table. It makes it pretty easy for us to calculate these x intervals that don't lie on perfect standard deviations. Let's try an example of it. So for 24, scientists conducted aerial surveys of a seal sanctuary and recorded the number x of seals they observed during each survey. The numbers of seals observed were normally distributed, with a mean of 73 seals and a standard deviation of 14.1 seals. Find the probability that at most 50 seals were observed during a randomly chosen survey. Okay, well, you'll notice with this 14.1 as a standard deviation, if we were to construct a picture of this bell curve, we'd have our 73 in the middle, and then we would move out one standard deviation. We would add 14.3, get 87, or sorry, 0.1, 87.1. We would subtract it away, get like 68.9. Clearly, this number 50 is not going to show up as one of our wedge dividing lines, one of our standard deviations. So we're going to come up with a z-score and use the table to answer this question. All right, so our z-score is going to equal the x value here, the 50 seals, minus our mean of 73 over our standard deviation of 14.1, and we get a z-score that is approximately negative 1.63. Okay, now remember, the z-score is the probability, or the table that we're using is answering the probability of less than this. So using the z-score, this at most is the same thing as less than or equal to, so we don't have to adjust the decimal that we will get. So if I go back to my table, negative 1.63. Okay, I'm at negative 1, and then 0.63 would fall in this column. We have to do a little bit of rounding here, but we get 0.0548. And that table is telling us the less than or equal to, so it's agreeing with this at most. So that probability of 0.0548 is our answer. Now, what do you mean we could have to adjust this? You know, we might need to do that. What if they said find the probability that at least 50 seals? So if we were trying to find that, we need the complement. So it would be 1 minus 0.0548, and that's how we would calculate our answer. We would get 0.9452. Okay, so we may have to do some little adjustments like that afterwards, but really all the math happened from finding the z-score and looking it up in the table. That is our final example here for section 11.1. Here's a look at your homework assignment.